talking about the single solution regime here. Again, it's m equals n over 3. And the space is basically 2 to the n over 3. The time is 2 to the 2n over 3. Basically, it's the same algorithm as the k-XOR, but it's unbalanced. So one group, like one function, you build a table for one function and you access it for each possible input of the second group of functions, f2 and f3. That's the basic algorithm. And then we saw how a non-trivial algorithm was actually still written here, sketched here on the board, and it allows you to have the same time complexity, but you can reduce the space complexity to 2n over 6. And that's in the kind of the regime where you expect a single solution on average. And in the regime, like where you increase the domain size to n over 2, and then you have a variance of this basic and improved space algorithm. So the basic algorithm basically reduces the problem to k-XOR, to this setting. So the time and memory is 2 to the n over 2. And the improved space is basically a variant of this algorithm. You just, with larger m, you can obtain 2 to the n over 2, so it's a better time complexity here. And I mean, for this, the optimal space complexity that we can do, we achieve space 2 to the n over 4, which is better than this algorithm. Okay, so basically that's a very quick summary of what we did this morning. And at the end of the talk, I started to kind of sketch applications for these algorithms. So I started to talk about like the ciphers GEA1 and GEA2. So the focus was actually on the GEA1 cipher, which the specification was only recently disclosed. So, okay, so let me just remind you, GEA1 has a 64-bit session key, and like this previous paper that was published last year described an attack which is based on a weakness in a cipher with time complexity to the 40, but kind of a lot of memory. Okay, and the weakness is believed to be intentional, and yeah. So in terms of in terms of techniques, the attack is based on the previous attack is based on the k-XOR. And basically what I'll show you is how to improve the memory of this attack. Of course, I'll have to describe this attack first before doing it, but then I'll show you how the memory can be improved using similar techniques that I described this morning. And therefore, I mean, as a result, we can run the attack on a laptop, so it's kind of nice. Okay, so now let me introduce the ciphers. So I started doing this, but I'll quickly recap. So basically, let's start with the initialization process. So this process takes as input 64-bit session key and 32-bit IV initial value. So it has two steps. The first step has input the key, of course, in the IV, and it uses it to produce, using some mapping, a 64-bit seed. And then the second step has input this seed and uses it to initialize a state. Okay, and the state has three registers, A, B, and C. So the size of A is, B and C are 31, 32, and 33 bits. Okay, so this mapping basically maps the seed to a 96-bit state, joint state of all the registers, and yeah, it's initialized using this mapping from which takes a 64-bit seed to a 96-bit state. Okay, that's the initialization, and then after you basically initialize the state, the initial state, you can start producing keystream and encrypting a packet. Okay, so before I show you how to encrypt a packet, let's define some notation so it will be easier. So let's, for example, take an internal state of this register A. Okay, so it's 31 bits, and we'll define a function fa applied to some internal state like this a underscore, and let's assume we only interested in, say, tau bits. Okay, so that's basically denotes the next tau output bits computed from this internal state. There's 31 bits of internal state. Okay, so how do you do it? Basically, you produce the bits one by one. So from I equals I up to tau, you apply some, the function here is not important, but you apply some Boolean function which takes 7 bits of the state at some positions which are not very important. And you apply it, this function, and you get a bit, and this is how you get the ith output bit this way, just by applying some function to 7 bits of this internal state. Okay, that's how you get the ith bit, and after you produce the ith bit, then you update the state. Okay, how do you update the state? So basically, it's just an LFSR. So an LFSR. So the way you produce Keystream is you have this internal state. Okay, and every clock cycle, you basically, these are the bits of the register. You just shift like every bit to the left. And then you need to compute this bit, right, in each clock cycle. And this bit is basically computed by XORing together a subset of the internal state bits. Okay, so it goes back in. Okay, that's an LFSR basically, and you repeat this process tau times to produce tau output bits. Okay, and of course I defined this just for the register A, but it's defined analogously for B and C. Okay, that's how you define outputs. That's how you output bits from the registers. And basically, the output bit of the cipher, at time I, you just XOR all the bits of the registers. Okay, that's how an output bit is produced. So with each clock cycle, each register is clocked once, and then you compute this function, FA, FB, and FC, and you XOR them to get the next output bit. Okay, any questions about this? Yes?
Are there locations of the bits that are going to be selected static, or does it vary with each instantiation?
No, the locations here are fixed. Okay, you can see them here. I'm not it doesn't really matter for this talk, so I'm not really telling you what are these locations. I mean, but the locations for the bits to compute F are just specified here. There are 7 fixed locations, and the location of the bits that are XORed are also specified here. But again, they won't really matter, and they're fixed. Okay. Any other questions? Okay, so we define this notation, you produce tau output bits from this internal state, and that's how you do it. Okay, so how do you encrypt a packet? So now basically you have initialized your internal state, and you want to ABC, and now you want to encrypt a packet of 12,800 bits. That's a plain text. So basically, you produce 12,800 bits of output, one by one, of course. So for each output bit, you just clock all the registers together, XOR their output bits, and you get the ZI, which is the ith bit of the keystream, and then you produce this Z, and you can compute XOR it with the plain text, which is the packet, and you get the ciphertext. Okay, that's how it works. That's how GEA1 works. Okay, any questions about this? Okay, so how does, without even talking about the weakness and the backdoor that I specified previously, so what's the strategy here to attack this cipher? Okay, so the attacker is going to obtain a 65 keystream bit, keystream, which we're going to denote Z, in some packet So how is going to do it? It's going to eavesdrop to the communication. It's going to get the ciphertext. Okay, and he needs to, like Z is equal to the plaintext XOR the ciphertext, right? That's, I mean, from this equation, you need to get 65 bits of Z, so you kind of need to get 65 bits of C and 65 bits of P in order to get these bits. And basically, so C you can obtain by eavesdropping to the channel, and you also need to obtain some plaintext bits. And this you can essentially do because there are some known plaintext that you can extract, for example, from the GPRS headers. Okay, so it's not difficult to do it. Just by eavesdropping to the communication, you can actually obtain 65 output stream bits of the cipher. It's not very difficult. Okay, and now, yeah.
Is it any 65 bits of the keystream, or we need like specific ones?
They need, I mean, a few of them need to be consecutive. There are some constraints on them, but I'm hiding this. I mean, I don't want to get into these small details.
Okay.
For now, let's think that you obtain 65 consecutive keystream bits at the beginning. Okay, I'm going to make this simplification. Okay, so now let's see what the attacker does. So given Z, given 65 output stream bits, it's going to run the attack and basically compute an internal state, which is a joint state of A, B, C, initial state that produces this keystream. So on average, like as I told you before, like there's a seed of size 64 bits that is used to initialize this state, this initial state. So essentially, this state has initial state has 2 to the 64 possible values, and now we obtain like 65 values of output. So on average, we expect like the correct solution. After we do the filtering, on average, we expect like only the correct solution to survive. So we can recover the initial state of GEA1, okay? And after we obtain the initial state of GEA1, we can actually, I'm not going to show you how to do it, but you can actually invert the initialization process and compute from the initial state. You can compute back the 64-bit seed that was used in the initialization, and you can actually invert the entire initialization process and derive the session key. Okay, and once you have the session key and you know the ciphertext just by eavesdropping, then you can compute the entire keystream Z for the entire GPRS session, which is composed of several packets and etc. And once you know C and Z, you can compute P. You can compute basically all the packets, and that's it. I mean, you've eavesdropped to the communication. Okay, so that's the basic setting. Any questions about this? Okay. So now, yeah, I'll tell you what is the weakness. Actually, I already told you in the morning, but let's see it again. So the weakness is in the initialization process of GPRS. So there were two steps. The first step was to compute the 64-bit seed from the key and IV, and the second step was to use the seed to initialize the 96-bit state by some linear mapping. Okay? These are the two steps, and the weakness is in the second step. And basically, we're looking at the joint state of registers A and C. So register A has 31 bits long, and register C is 33 bits long. So their joint state has like 2 to the 64 possible values. And so that's kind of what we would expect. The initial state of these two registers to have also 2 to the 64 possible values. That's kind of what you would expect. But actually, this linear map is kind of degenerate in the following sense. So the joint state of A and C, which is 64 bits long, can only obtain 2 to the 40 initial values out of the 2 to the 64 possible ones. Okay, that's the backdoor. That's kind of the weakness of the cipher.
So you think it was introduced on purpose because to get a 64 bits image, the only thing that you have to do is choose an invertible matrix there, because you said M was a linear map.
So M is invertible. I mean, M is if you look at each register, like each register can obtain all possible values. But when you look at pairs of registers, when you look at the pair of A and C, they by some magic, they can only obtain, both the states can only obtain 2 to the 40 possible values out of 2 to the 64. And of course, the authors, I mean, this is not my result. The authors of the paper conjectured that it was actually intentional. This backdoor was intentional in order to weaken the cipher. Okay, that was the assumption here. Of course, we don't know. I mean,
but how can you do this intentional? Because at that time you didn't have the computational power to, let's say, compute 2 to the 64 combination of the initial states.
No, so I mean, if you're a designer, you would design if you want to embed the backdoor, you would design this this mapping M such that the states A and C, if you project like this initialization mapping on the states A and C, then this mapping, then projected mapping won't have the full rank. Okay, then that's how you would design the cipher if you wanted to plant a backdoor, and that's probably what they did. I mean, any other questions? Yeah.
And how was this bias discovered?
So again, it's not my result, but there were 8 authors. I think Gaetan is one of them. He's sitting in the room. But basically, I think I mean, the specification was disclosed to them, and they started running some tests, and they just saw that this mapping, when you restrict it to these 2 registers, it's degenerate. It's yeah, it's essentially like if you look at it from a linear algebra perspective, we're looking at the projection of this mapping, of the image of this mapping to registers A and C, and its dimension is only 40 instead of 64. And basically ran some tests, and it's not very difficult to see because, I mean, once you know this mapping M, it's just some linear mapping, and you can compute this image, and you can, I mean, the base for this image, and you can detect this. Okay?
Thanks.
Any other question?
I mean, perhaps if you pick a transformation at random, what's the chance of having it?
Okay, so the authors ran some tests, and they basically concluded that the chance is very, very, very small. Like, I don't know, 1 in a few millions, or I don't know. It's exceptionally small. So it's very, very unlikely that it would happen by chance. Okay, so you think of this, this is basically a random mapping. I mean, if you pick a random mapping, then from 64 bits to 64 bits, then the probability it would have dimension 40 is I mean, it's completely negligible. I mean, okay. Okay, so let's see now how do we exploit this weakness in an attack. So the attack is basically, is essentially based on k-XOR. Okay, that's how we run the attack. So let's, yeah, so that's the attack, and let's do it on the board. Okay, so we have this function fb, okay, which basically takes an internal state like b underscore of 31 bits, and here I need to produce like 65 bits because that's the length of z. That's like what I want to do. And why do I want to do this? Basically, what we want to do now, okay, I should have said it. Basically, what we want to do is we want to search for some internal state, initial state, ABC, such that FA applied to A, XOR FB applied to B, XOR FC applied to C is equal to this given output Z. Okay, that's basically a 3 XOR problem, right? Basically a 3 XOR problem, just F1, F2, and F3, the random functions that I defined previously, you replace them with the functions of the registers, like the outputs of the registers, and now it's basically a 3 XOR problem. And you want to solve a 3 XOR problem. Of course, I mean, what we want to exploit here is that there are actually internal relations between the functions. I mean, they're not independent functions, so the function FA and FC are dependent because the joint state of A and C can only assume 2 to the 40 values instead of 2 to the 64, and we want to exploit that in an attack. That's what we're going to do. Okay, but basically this is a 3 XOR problem. Okay, and if you tweak things around, then what we want to find is that FA applied to X or FC applied to C or Z is equal to FB applied to B. Okay, and that's the relation that we're going to look for. I mean, we're going to look for states, initial states A, B, and C, A, B, and C, yeah, that satisfy this relation. And once we know the 65 bits Z, output bits. Okay, so essentially we need to produce like 65 bits from each of one of these initial states, and we want to find states that satisfy this relation. Okay, that's the goal. Okay, so now how does the attack work? So we have this FB. So what's the domain size here? It's the number of internal size, number of possible internal states of register B. So it's 2 to the 31. And now we're looking at the joint state of A and C. So we'll have another kind of function here, which I'm going to call FAC. Which how is it defined? It's just FA applied to A, XOR FC applied to C. That's the second function, and the domain size here, just by the weakness, is 2 to the 4. Sorry, it's 2 to the 32 here. That's the register B, and the domain size here is 2 to the 40. Right? That's the weakness that I showed you. And now I want to satisfy this relation. Okay, so what I want to satisfy is this XOR Z is equal to FB applied to B. Okay, so what I'm going to do is I'm going to compute a table for this function, right, for all possible internal states. So I'm going to have a table which maps internal states B to FB applied to the internal state. And this table is going to be of size 2 to the 32. Okay, and now what I'm going to do is I'm going to basically look up this relation. So I'm going to, for every possible AC state, so there are 2 to the 40 states, possible states, just by the weakness, I'm going to, for every possible state, I'm going to compute this expression and just look for, a row here that matches. And once I find the row by the arguments that I said, with good chance that then I recovered the internal state. Just because there are 2 to the 64 possible internal states, ABC, and you have 65 bits. So I'm computing every function here. It's not written, but yeah, it's prefix 65. I didn't write it explicitly, but it should be like prefixes here should be like 65 bits. Okay.
So in this case, we don't need Oracle access to the functions. We just evaluate them ourselves.
Yeah, but that's usually what happens. I mean, usually the oracles are. When you talk about real crypto systems, you don't have oracles. You compute the function yourself. That's usually what happens. When you model the problem as a k-XOR or 3 XOR problem, then you talk about oracles because you want to be generic. But it's always the case when you apply things in practice, then you implement the oracles yourself.
Okay, so there is no need to interact with the with the crypto system in practice to obtain this?
No, you implement it
You just-
yourself, and yeah, you have the specification. You just run the LFSR yourself, and compute this function f, and compute the output bits, and basically. Yeah.
Makes sense. Thank you.
Okay, any other question? Okay, so basically that's that's the attack. I mean, that's it's kind of a simplified version of the attack. And why is it simplified? I think still there's one thing missing here there's one fishy thing here. Note that let's compute the expected number of solutions that you would get from this procedure. So how many internal states are we actually computing? So for B, we have like 2 to the 32. That's what's written here, what I've also written on the blackboard. And the joint state of A and C has 2 to the 40 possible values. So like if you compute like how many internal states we are actually computing here, it's 2 to the 72 because it's 2 to the 40 times 2 to the 32. Okay, and then the number of expected solution you would get from this procedure is 2 to the 32 plus 40 minus 65 because you have 65-bit filtering condition on the Z keystream, and then you get 2 to the 7 possible solution, which is actually larger than 1. Okay, so something doesn't really add up here. So we're kind of missing conditions. Okay, so something is not completely right here. Okay, now I'll show you how to correct this in a few minutes. Okay, that's one thing that we should, at least explain. Another thing that, note that it's not exactly a random XOR problem for various reasons. One reason is that we know that a solution always exists, right? Because if you obtain the right keystream, then there is a right state, like initial state ABC, that actually produces this keystream. Okay, that's one thing that we should keep in mind. Okay, so there are a few differences between this problem and like the nice modeling of the problem that I described this morning. Okay, but if you kind of ignore these subtleties, then basically, and I'll show you how to correct this in a few seconds, basically you get a time complexity of 2 to the 40, which is basically the internal states that you enumerate of A and C that you enumerate here, and the space complexity is just building this table here. Size 2 to the 32 words, and if you do the calculation, it's roughly 45 gigabytes. Okay, that's the attack. Yes.
So I was wondering whether, so we know that A and C, when we look at them, it's like a smaller space, but is it always easy to iterate that space?
Yeah, it's easy because it's a linear subspace. So you have a basis, and it's very easy to produce elements in the spaces just by XORing together the basis vectors. It's very easy, okay? Because it's a linear mapping. Other questions? Okay, so I described you kind of a simplified version of the attack. So now I have basically 2 remaining goals. The first is to show you how to obtain better filtering of the states, because something didn't add up here. I mean, we're kind of missing something here in this analysis, and I'll show you how to fill the gap. The second thing is like what I promised. So I want to reduce the memory complexity from like 2 to the 32 words, and still haven't shown you how to do this. Okay, so why, let me just say a few motivations. Why do we want to reduce the memory complexity? First of all, it's nice. Yeah, it's a nice, nice applications of the generic algorithms that I described this morning. And in general, I think it's, if you look back at the early 2000s, I mean, this high memory attack, it's still not trivial to run. It's especially if you're kind of trying to eavesdrop to communication at scale. I mean, you need to allocate a lot of memory, and definitely in that time, it was not trivial. So it did matter, at least at that time. And I think in general, it's better to understand, the exact security of ciphers that were used in practice. I mean, it's kind of useful and important. Okay, so it's, I think that offers enough motivation. Okay, Okay, so now, so let's start to work on these goals. So the first goal is to actually obtain better filtering for the attack. So with the analysis that I did, actually there are more than one solution on average that you would get from this attack, and that's really not how it should be. So in order to obtain better filtering, actually we're going to exploit linear relations that exist between the internal state B and the internal states of A and C, and the joint internal states of A and C. Okay, so let me tell you why these linear relations exist. I mean, it's not obvious that in general that they would exist, but in general, let's see why. So basically, remember that the dimension of the mapping, it maps a 64-bit state to a 96-bit internal state. Okay, so the dimension of the image is 64 because it maps a 64-bit state, right? On the other hand, the dimension of the image of M, projected to AC, is 40, right? And the dimension of the image of M projected to B is 32. Okay, so if you add up these two numbers, you get 72. Okay, and basically this means that there are linear relations between the internal state B and the joint state of A and C. Okay, they're not independent. There are some linear relations between them. Okay, I'm not going to prove it formally, but I think this kind of explains you why this happens. And in particular, there is kind of a shared subspace. I'll call it shared subspace, and I'll denote it by U, which is contained in the image of this mapping, which is of dimension 72 minus 64, which is 8. Okay, so there is a kind of 8 common linear relations between this state and this joint internal states of A and C. Okay, and given this, what we can do is the following. So we can decompose the image of the mapping M projected to B into a direct sum of kind of two subspaces. The subspace U, this common subspace projected to B, or some other subspace. I don't care what it is, but I know its dimension is 32, which is the original dimension of this, minus the dimension of U projected to B, which is 8, so you get dimension 24 here. It doesn't really matter what is this subspace, but we know that its dimension is 24. And similarly, you can kind of write the image of this linear mapping projected to AC as this shared subspace projected to A and C, direct sum with this other subspace V2. And the dimension of V2 is just 40, which is the joint dimension of the image of A and C, minus the dimension of UAC, which is 8, so you get 32 here. Okay, is this clear? Okay, so this is actually our missing, what we're missing in the filtering. And not only that, this will actually, as we will see, it actually gives you, allows you to improve the space complexity quite easily. I mean, without even doing much. Okay, so now I'll show you how to reduce the memory complexity by a factor of 256 by exploiting these linear relations between the joint internal states. So the basic idea is that now we can kind of divide our attack. We have this large meet in the middle attack, right? Its complexity is 2 to the 40 and so forth. For each, and I like it consumed 2 to the 32 memory. Now that we have this shared subspace, we kind of can iterate it over it in an outer loop. And for each element of the shared subspace, we can run kind of a smaller meet in the middle attack, which takes time complexity 2 to the 32. And the memory complexity is reduced also by 2 to the 8. So from 2 to the 32, it will be 2 to the 24. Okay, so basically that's how it's going to be. So let me just draw it here. So basically what's going on here is the following. So we have this FA and FAC. So now that I'm telling you, okay, we have this common subspace. Basically, this common subspace allows you to divide this kind of this domain into 2 to the 8 pieces, right? So each piece is it's like a vector in U, in like big U, in this shared subspace. Okay, so we're going to run the attack separately for each vector in the subspace. So now, how does it work? Well, for each vector U in the subspace, for each piece, we're going to actually compute a smaller table because each piece here is only of size 2 to the 24. Okay, so the table here, instead of being of size 2 to the 32, is going to be only 2 to the 24. Okay, and similar thing goes here for FAC. So instead of working over 2 to the 40, we'll work in pieces, so each piece will be of size 2 to the 32. Okay, so basically we're running 2 to the 8 smaller meet-in-the-middle attacks, and this will allow us to reduce the space complexity by 2 to the 8. Okay, so basically how does the attack work? So for each U in this common shared subspace U, okay, so now we have an outer loop. So we do a small meet-in-the-middle attack. So now for each V in the subspace V1, okay, now we can compute the internal state B just by XORing together this U projected to B and V1. Okay, and then we're building our smaller table here, which is of size 2 to the 24. Okay, and now we do similar thing for FAC. So for each V in V2, okay, so the dimension of V2 is 32, so it's 2 to the 32 steps here. We compute the joint state A and C just by this relation, by XORing two vectors. So U projected to AC XOR this current V2, and we search this relation in TB. Okay, so it's basically same attack as before, just divided into 2 to the 8 pieces. Okay, so we're building a smaller table here. We're just building it 2 to the 8 times and so forth, but complexity remains, time complexity remains the same. Memory complexity reduced by a factor of 2 to the 8. Any questions about this? Okay, now you can see that the number of filters solution also adds up. We solved kind of, in a sense, we solved two problems at the same time. And why is that? Well, how many states are we iterating over now? We have this common subspace of 8, of dimension 8. And now here we're iterating over subspace of dimension 24, right? And here we're iterating over subspace of dimension 32. So the number of internal states that we're iterating over, if you sum everything up, it's 2 to the 8 plus 24 plus 32. And now it adds up to 2 to the 64, as we would expect. And we're kind of filtering it on 65 bits. So the number of expected solution is 2 to the minus 1, is half. So of course we expect the right solution to, the correct solution to survive. But besides that, we don't really expect other solutions. And yeah, that's how you also solve the problem with the filtering. Any questions about this? Okay, so the complexity is 2 to the 40, time complexity. It remains 2 to the 40 because, the heavy step is here. It's 2 to the 32. And we do it 2 to the 8 times, so time complexity 2 to the 40. And the space is reduced to 2 to the 24 words, which is 256 megabytes, basically. Okay, so now we want to get a bit greedy. We want to actually reduce the memory further. Yeah.
Why is it actually 2 to the -1 now instead of 2 to the 0? Just one solution?
Because we're iterating over 2 to the 64 internal states, and we have a 65-bit filtering condition.
So would the attack fail half of the times, or?
No. So I mean, here we're actually we're not counting. Think of it as we're not counting the right solution. I mean, it should be +1 really, because the right solution always survives. I mean, the right solution cannot be eliminated. So here we're actually counting how many like parasite solutions you would have on average, and the number is like half. So you think of it like most of the time we won't have any parasite solution, so we only get the right solution.
The right. Okay, makes sense. Thanks.
Any other questions? Okay, so like I said, we want to be a bit greedy, and we want to reduce the memory further. Maybe we want like the memory to fit in cache or something like that. So it would be nice. And yeah, so that's the question that we're asking. And well, the answer, it turns out to be yes. You can reduce it further. And the thing here to notice is that as like the intuition that I gave you in the morning with k-XOR problem, we had like 2 steps, and the steps were not balanced, right? And the same thing actually happens here, okay? And right, the steps are not balanced. You look at that first step here. So the dimension of V1 is 24, right? So fix some U. So the dimension of V1 is 64. So the time complexity of the first step is 2 to the 24. And the space complexity is 2 to the 24 just because we're building a table for all V1 in this big subspace V1. Okay, on the other hand, this V2 subspace is of dimension 32. And here we're not using really any space. So the time complexity of this step is 2 to the 32. I mean, and the space is negligible. So once again, you see that we have 2 steps and they're not balanced. So maybe this can hint that we can actually improve the time complexity further. Okay, so now we'll try to kind of use the 3 k-XOR techniques that we learned in the morning that maybe to improve the memory complexity further. Okay, so in particular, we try to use the like the clamping through precomputation technique, similarly to what we did with the 3 k-XOR algorithms. Okay, so that's the original algorithm that has time complexity of 2 to the 24. Okay, and here is a kind of a suggestion for an improved algorithm. So what does the clamping through precomputation technique do? You basically fix some prefix. Okay, so it's going to be, let's say, 5 bits. I'm not going to tell you exactly why 5 bits, but let's say we fix some prefix for the output of this table. So now now we add an extra condition, right? So what we're doing here, let's compare this step, the first step. So the first step, we're doing exactly the same, but now we're adding some additional filter, and we want that FB applied to B, prefix of 5 bits is equal to this prefix T. And we're going to iterate basically over all prefixes. So essentially, this will give us a smaller table by a factor of 2 to the 5. Because we fixed just some 5-bit output prefix. Okay, so yeah, we're trying this. If you go back to the 3 k-XOR algorithms, that's exactly what we did. I mean, that's the kind of the clamping through precomputation technique. Okay, that's relatively straightforward. We're not doing anything too interesting here. Okay, and the second step, what we can do. Okay, now I'm just trying to massage this second step. Okay, so the extra thing that we ask is instead of just looking like we compute this AC state, which is I don't know, XOR of 2 vectors. Okay, so instead of just looking it up in the table, like if this is a right XOR solution, then we look at the 5-bit prefix, and it should equal to T, right? So the output prefix here should be equal to the output prefix here. And only if it equals to the output prefix here, then we actually search the table. Okay, so basically that's a kind of a straightforward attempt to apply the clamping through precomputation technique to this algorithm. Okay, we're just taking an outer loop here over the like a 5-bit output prefix. Okay, and we adjust the steps accordingly. Any questions about this? We really didn't do anything too interesting here. Okay, so the space complexity is going to be reduced. I think it's kind of clear because here we're just adding, like, on average, like 2 to the 5, I mean, a fraction of 2 to the minus 5 vectors. So it's going to be, because we're checking this output bit condition, so the space complexity is going to be 2 to the 24 as before, minus 5, so it's 2 to the 19, okay? It's going to be reduced. Okay, however, there's a problem, right? What's the problem? We really didn't optimize the second step. We really didn't do anything interesting here. I mean, we're just iterating over the entire subspace V2 as before, and computing the state AC, and then checking some condition, and then searching the table. I mean, but we're still iterating over this entire subspace, so we're not doing really anything really interesting here. The time complexity of the second step is going to remain the same. We didn't do anything really non-trivial here. So the time complexity of the second step is going to remain 2 to the 32, but we're now added an outer loop of 2 to the 5, right? So now the overall complexity is going to grow by this factor of 2 to the 5. So it's going to be 2 to the 45. So that's not what we want. We want to keep the time complexity the same, but reduce the memory complexity. Okay, and we didn't achieve this by this algorithm because we really didn't do anything too interesting in this step. I mean, we should really use the memory to kind of iterate, not to iterate over all V2. We should iterate over only the vectors that satisfy this condition in advance. We kind of should do something clever here to exploit this additional condition. We cannot just, add an outer loop and expect the time complexity to drop. Okay, this does not work. Okay, any questions about this? Okay, so basically what we need is for this second step to run in time, we need to exploit this additional condition to make the complexity of the second step drop to 2 to the 27 in order for this to add up. Okay, but actually it's not clear how to do this, to be honest. It's from the description up to now, it's not clear how to do this, how to kind of, satisfy this condition and only time to the 27, because the dimension of V2 that we need to kind of iterate over is 32. I mean, another thing that you may want to do, perhaps can do, is to, if you go back to the, state of GA1, maybe you can somehow cleverly iterate over V2 by, just by decomposing it into its like projection on A and projection on C, and maybe you can do something clever here. Unfortunately, this doesn't also seem to work because the size of A is 31 bits and the size of C is 33 bits. So it's not clear how to actually reduce this complexity. Okay, it's not clear. It's not trivial at all. But actually, yeah, it can be done. So I'm not going to show you how exactly it can be done. This is a bit more technical and perhaps not fitting, I think, for this talk, but I'll give you kind of the main idea. So you can actually implement this step in time complexity 2 to the 27 and really negligible memory. And the idea, okay, what the attack actually does is to enumerate over all the joint states of A and C. satisfying this condition without exhausting V2, without like going over all the vectors in V2. And the main observation for this is to actually look at this is the part that I'm not going to expand on. I mean, if you're interested, then you can look at the paper. But essentially, the point is that actually, if you look at the 5-bit output prefix of A, of like applied to a state A, that it actually does not depend on all the bits of A. It depends only on 26 bits. I mean, and like for 1 bit, if you want 1-bit output prefix, then like it's output by this function f that depends only on 7 bits of A. And if you want to compute a 5-bit output prefix, then you do the calculation and you see that it only depends on 26 bits of A. And similarly, the 5-bit output prefix of FC applied to C only depends on 22 bits of C. So we actually can do this step by exploiting like the internal structure of the registers. Okay, you kind of exploit the internal structure of the functions in order to do this and to implement the step more efficiently. Okay, so I'm not going to expand exactly on how to do this. Like I said, it's too technical, I think, for a talk like this. But basically, if you're interested, you can look at the paper. Basically, you do basically another meet-in-the-middle attack and use, again, some more linear algebra to obtain it. Okay, so like I said, I'm not going to go deeper into this. Are there any questions?
So is this main observation the reason why you chose the prefix length of 5 bits, or?
Yeah, that's the reason. If you look carefully, then you see that the 5-bit output prefix depends. I mean, like the complexity of the attack is it's 26 bits. I mean, this 5-bit output prefix depends on 26 bits of A. And if you go further, if you look at the 6-bit output prefix, then it already depends on like, I don't know, 29 bits of A. And then you don't get the right complexity here. So 5 bits is kind of the maximal that you get, and you can still have time complexity of 2 to the 40. I mean, there are some kind of intricate relations here that that make us choose the 5 bits. I mean, it's not just a magic number. I mean, I'm not really explaining why, but yeah, it depends on the number of output bits that this prefix depends on.
Thank you.
Any other questions? Okay, so I'm basically done with explaining the GEA1 attack. So Jean-Paul, how much time do I have? 25? Oh, 35, okay. So I think what I'll do is I plan to do the fork XOR and then have an additional application to the GA2. I'm not going to do it. I'm going to skip to a completely, completely change gears. I'm going to switch to a more theoretical topic. So yeah, let me just skip over the slides. For fork XOR, I'll put the slides on because I really want, yeah, it's going to take me some time, and maybe at the end I can do it. But fork XOR, the techniques are kind of related to the 3 XORs. That's why I prefer to skip this version. Of course, it's interesting on its own. I'm not saying it's not interesting, but I just want to show you different results. This one is kind of less related, and it's it's kind of different. So that's why I prefer to spend more time on this. Okay. So let me quickly. So now we're back at the 3 XOR setting. So let me just remind you, we had like 2 algorithms. Not 2, we had more, but we're back at this single space, single solution regime. Okay, and we had this algorithm. Remember, we were kind of, we had these functions. We're building smaller tables. for each function by iterating over prefixes, and then we kind of merge them together, and we hope for a 3 XOR solution. And this was kind of the space optimized algorithm that has a time complexity of 2 to the 2n over 3. Okay, actually, I'm not going to care about space complexity in this part. I'm just going to care about time complexity. And we had like another variant where you increase the domain size of the functions to m over 2. Okay, and we had like a variant of basically the same algorithm that obtains time complexity 2 to the n over 2. Okay, so it improves upon the previous algorithm. And I think that's what Yevgeny actually mentioned. He probably guessed, and he guessed correctly, that you can, of course, have an algorithm that can exploit any domain size between n over 3 and n over 2. So there's a kind of a trade-off algorithm. Okay, I'm not going to analyze it. Basically, it's the same structure. I mean, it's the same thing. You just have now a parameter of the domain size of the functions between n over 3 and n over 2. And it allows you to kind of obtain a trade-off between these two extreme points. Okay, so if you do the calculation, and again, I'm not going to do it because we did something very similar, then you get a trade-off. You get this trade-off of t times 2 to the m equals 2 to the n. So if you plug in here m equals n over 2, that's the kind of regime where you have many solutions, then the time complexity is 2 to the n over 2. And that is what we obtained with the algorithm where we have many solutions. And if you obtain here m, if you plug in here m equals n over 3, you get 2 to the 2n. 2 to the 2n divided by 3. And this is kind of the basic algorithm that we had. So we have a trade-off. For each m, we get like a time complexity, a different time complexity. Okay, so in the single solution regime, we have time complexity 2 to the 2n, and in general, 2 to the 2n over 3, and in general, we obtain this trade-off. And the complexity in general depends on basically how many solutions we have. And that's basically the trade-off curve, right? For 2 to the 2n over, this is 2 to the m, right? The domain, the size of the domains of the function, of the functions, f1, f2, and f3, this is the time complexity. So for 2 to the 2n over 3 domain size, we have this complexity. And for 2 to the n over 2, we have, for m equals n over 2, we have time complexity of this point, 2 to the n over 2. This is basically a trade-off curve. Okay, so essentially I'm going to call this regime where you have a single solution on average, where m equals n over 3, or in general for k-XOR n over k, we're going to call it the sparse regime. Okay, like you have a sparse, like the solutions are sparse. And when you have more, I mean, the problem gets denser. You have more solutions, like when the domain size is bigger. And now we ask the following, I mean, natural questions. Is this trade-off optimal? Like, can you go below this line? Okay, that's the question that we're going to ask. Okay, in particular, for example, can we obtain 2 to the n over 2 time, but with domain size less than n over 2? Can we kind of push this point to the left? Okay, can we do it? I mean, that's an interesting question to ask. Okay, so kind of a recent result. We showed the following, statement. It's not very formal, but basically what we do is we prove the following. So the results is stated as follows. If for the sparse regime, meaning that m equals n over 3, where we have a single solution on average, if this algorithm is optimal, I mean, just a basic algorithm that obtains time complexity of 2 to the 2n over 3, if this single algorithm is optimal, then the entire curve here is optimal. I mean, you cannot go below this curve. Okay? So that's the result. Okay, so basically, if you conjecture just that this algorithm is optimal, then you get the entire curve. Okay, and I should say that the result is actually much more general. We obtained the condition optimality of full trade-offs for k equals 3, 4, and 5. I didn't talk about 4 and 5, but there are similar curves for 4 and 5, you can imagine. And for k larger than 5, then we obtain, like there is also a trade-off obviously for k larger than 5, then we obtain an optimal trade-off, but for a more limited range of parameters. I mean, it's not for the full range of parameters. And we also obtain similar results for k-sum. But I'm just going to focus on this simple trade-off in the rest of the talk, just for simplicity. Okay, in particular, again, I'm going to simplify even more. So what I want to show now is that if this point is optimal, if like t to the 2n over 3 for the sparse regime algorithm is optimal, if this point is optimal, then no algorithm can obtain like time complexity 2 to the n over 2, like given input size of 2 to the 0.49 m instead of like 2 to the 0.5n. Like you cannot obtain this point. What I'm showing is that if you cannot obtain better than this in the sparse regime, if you cannot push this point down, then you cannot like kind of push this point to the left. Okay, this is the kind of the result that I'm going to focus on. Okay, and for this I'm going to switch a bit notation because up to now I talked about upper bounds like algorithms, and now I'm talking about lower bounds. I mean, I now have to kind of look at the problem from a different perspective. So it's not going to be convenient to look for like to work with the standard k-XOR standard notation for k-XOR. I'm going to switch notation a bit. So the first thing I'm going to do is I'm going to switch from description of the problem where we have 3 functions and we're looking for like input to 3 independent functions to a problem where we have just 1 function. And we're looking for 3 inputs for the same function that XOR to 0. Well, like x1, x2, and x3 that are input to this function such that each, the XOR here is equal to 0. So now we have just 1 function. And you can show that these 2 versions where we have 3 functions or you have 1 function, they are basically equivalent. I mean, up to constants, they are essentially equivalent. Okay, it's not difficult to show, but yeah, I won't do it, but it's not you have reduction, it's not difficult to show. Another thing, okay, another formulation, switch of formulation, is that instead of like talking about functions, we can assume that this function f is actually given like a Boolean matrix. Like this function f takes you from as domain size of 2 to the n over 3, and it spits back, I mean, vectors of size n. You can think of this entire function being encoded as a matrix of dimensions 2 to the n over 3 times n. Okay, that's the same thing, just a different notation. Okay, so we're going to denote the ith row of the matrix by xi. Okay, now the k-XOR problem is the follows. Okay, it's the same for equivalent formulation. So now we're given access to some Boolean matrix of dimensions 2 to the n over 3 times n. Okay, so we're going to denote it by x. And now the goal is to find 3 distinct rows, I, j, and k, of the matrix, such that the row vectors of length n bits sum to 0. xi, XOR xj, XOR xk is equal to 0. That's essentially an equivalent formulation to the 3-sum problem. Any questions about this? We just switched formulations. We didn't really do anything too interesting here, but it's going to be more convenient to work this way. Okay, so now remember what we want to do. We want to show that if kind of the algorithm for the sparse regime is optimal, then kind of no algorithm can obtain 2 to the n over 2 with input size like this is quite dense, time complexity 2 to the n over 2 with input size to the 0.49n. Okay, so how are we going to do it? We're going to do this by reduction. So the proof is going to be by reduction. So like we're going to assume in contradiction that we have this algorithm, like in the dense regime, like it gets a matrix Y of dimension 2 to the 0.49 n prime times n primes. So it gets this input, and it can like produce outputs like k-XORs in time complexity to the n prime over 2. So we assume in contradiction that we have this this red algorithm for the dense regime. Okay, now we want to kind of show that this sparse regime, now we want to design from it an algorithm for the sparse regime that does better than the trivial algorithm, that has time complexity better than 2 to the n over 3. Okay, so we're going to build from this algorithm an algorithm A in the sparse regime that gets a matrix in the sparse regime of dimensions 2 to the n over 3 times 2, times n. Okay, and it spits out a 3 XOR for the sparse regime. Okay, so we want to design this reduction. Okay, so is this setting clear? Okay, so yeah, okay, so we assume again that we're given an algorithm B that solves the 3 XOR giving kind of dense instance with this dimensions and time complexity 2 to the n prime over 2. Let's say that it does so in probability, say, half. And we want to construct an algorithm for the sparse regime that solves 3 XOR given a sparse instance, like with these dimensions. And its time complexity is going to be slightly below 2 to the 2n over 3. So it's going to be 2 to the 0.66n. So it's slightly below 2 to the 2n divided by 3. And let's say we want to solve the problem with probability 0.1. So that's already a contradiction, because the time complexity here is smaller than the assumption. I mean, the assumption is that the sparse algorithm is optimal, and we were kind of disproving it. So, okay, so now the goal is to design this algorithm, right? We need to design the sparse algorithm A. Okay, so in other words, we are given a sparse instance, and we want to construct a dense instance with many solutions and feed it to B. We're going to get like a solution for the dense problem, and we want to kind of pull back a solution for the sparse problem from it. Okay, that's the goal. Okay, that's what we want to do. So the question is, how can we do it? I mean, how can we, given a sparse instance, construct an instance with more solutions, like kind of, apply B, get like an instance, get like a 3 XOR for the dense instance with many solutions, and then kind of solve the sparse instance. That's the thing that we're trying to do. Okay, so, I mean, you have to think about it for a while, and the idea is basically to truncate columns of the matrix. What does it mean? Okay, so here's a picture. So think of the blue matrix. That's a sparse instance. So it has 2 to the n over 3 rows and n columns. And now we're going to kind of truncate, we're going to throw away columns. So now let's look of this thinner matrix with less columns. So this thinner matrix obviously has more solutions because there are less constraints, right? Like there could be, I don't know, 3 vectors here that XOR to 0, but maybe they don't XOR to 0 on the full row. So we're kind of artificially creating more solutions here. Okay, so that's basically the reduction. Okay, and basically you need to create like we have an instance with this dimension, and you need to create an instance with this dimension. Okay, and you need to kind of work out the parameters here, and we're not truncating rows, we're keeping the number of rows the same. So this dimension should be equal to this dimension, and we need to solve some equation. And you get that basically n prime here, which is kind of the number of rows in the and the dense matrix is equal to 0.68n. I mean, that's just what we get. So it means that basically in order to apply this B, this algorithm B, we need to truncate this part, and we need to remain with basically 0.68n rows, columns, with this matrix. Okay? That's basically what we need to do to run B. Okay, so now how does the algorithm A work? We still want to solve the sparse instance using the algorithm for B for the dense instance. So A is going to truncate these, I mean, it's going to only leave n prime rows, which is 0.68n, columns of this matrix. So we have this truncated matrix. We want to feed it to B. And now B gives us like 3 rows on the like thinner matrix that XOR to 0. And now what we want to do, what we hope for, is like if you look at right of the remainder here, we want, if we're lucky, the remainder here will also XOR to 0, and then we have a 3 XOR for the sparse instance. Right? If we're lucky, then this might happen. Okay, that's what we hope for. Okay, so basically, we feed like this thin matrix to B. We check whether these 3 vectors, I mean, these lengthened vectors now XOR to 0, and if so, we have an output for the 3 XOR solution. And what's the probability of this? Well, the probability of this, I mean, B didn't even look at these. It's not even given these dotted vectors, the remainder of the vectors. So what's the probability of these 3 remainders XORing to 0? Well, it's 2 to the 0.68n minus n. It's just the remainder here. It's 2 to the minus, like the remainder, what's remaining here. So it's basically 2 to the minus 32n. So the probability that from one execution of B will get a 3 XOR solution is 2 to the minus 32n. Okay, so what you can do, you don't want, this is not a good success probability. You want to amplify the success probability. So what are you going to do? Basically, you kind of have to repeat the process. I mean, there's not much you can do. You have this black box, and it's only given you a good solution with low probability, and you're going to have to apply it once more, and so forth. So basically, we're going to apply this black box around, it's not exact, but 2 to the 0.32n times. For example, with different truncations. We truncate it once, like with the left columns, maybe we try the right columns, we try other columns, etc. Okay. So now we kind of define the algorithm A and the expected number of solutions that will be output by A. So if we repeat it 2 to the 32n times, the probability of being correct is 2 to the minus 32n. So the expected number of solutions that will be output by our algorithm A is 1. Okay, so kind of looks okay. And if you look at the time complexity of A, okay, so it's 2 to the 32, 2 to 0.32n times the time complexity of B, right? Because we're running B 2 to the 0.32n times, and that's the time complexity. And if you plug in the parameters, then you see that we get what we want. We get this time complexity. Okay, that's not very difficult to see. So the time complexity of the algorithm that I showed you is good. But there's one thing missing here. Okay, there's one thing missing. What's the problem here? And if someone can quickly say. Okay, so there's one thing that I haven't showed you.
I don't know, maybe when you truncate the columns, can you be sure that it's a random instance of Y, or?
It's a random instance because we're truncating a random instance, and it's a random instance. I mean, each instance is indeed random, but you're kind of in the right direction. I mean, it's not, you're not very far. You just need to think a bit more. Let's truncate randomly. Yeah. The instances are still very correlated. Exactly. Okay, the instances might be correlated. Okay, and we actually need to compute the success probability here. I mean, I said that the expected number of solutions output by A is 1, and that's correct. But it doesn't mean that the success probability of the algorithm to find the k-XOR solution is a constant. That it's not the same thing. Okay, and that's crucial here. Okay, and the thing is that the runs are highly dependent. I mean, we kind of, you know, it's not sufficient to compute the expected number of solutions. You actually need to, what we need is the following, is that the probability that A succeeds, I mean, the probability that it outputs more than one solution is constant. And if the runs are indeed independent, then this would happen. But we didn't say that the runs are independent. And the problem here is that B can be malicious. We don't know how it works, right? It could be malicious, and it could correlate its answers. And in particular, it can actually output solutions from a very small subset. And if it does so, you think about it, you run B, you get a k-XOR solution for the dense instance, and it's not good enough. Like the probability that it will be good enough is very small. And you run it again, and you get the same solution, so you're not gaining anything. Okay, the problem is that I haven't shown you that the instances are independent. And in fact, they're not. In fact, B can cheat here quite easily, okay, with the algorithm that I defined. Okay, so for example, here's an algorithm for cheating B that would actually break this analysis. And for example, B can output the first lexicographic k-XOR in this matrix that XORs to 0. Like the first lexicographic yijk such that the k-XORs are equal, such that there is a k-XOR. Okay, you can do this because we're not restricting it in any way. Okay, you can read the entire output. It has enough time, and it could, I don't know, select k-XOR the way that it wants. Okay, and the thing to note is that this is a dense solution with many k-XORs. Okay, and the sparse solution, like by definition, only has one k-XOR. And note that this k-XOR, like if you look at its lexicographic ordering, it's not going to be, I mean, on average, it's not going to be in the beginning, it's going to be somewhere in the middle. And the probability that, I mean, you truncate at different places, but the k-XOR, I mean, you haven't shuffled the rows, so the k-XOR lexicographic ordering is going to remain roughly the same. So if the k-XOR, like the k-XOR solution of the sparse instance is not by chance at the beginning, it's actually never going to be output. Okay? And this probability that A succeeds actually, I mean, in each iteration, in each run, in each truncation, it succeeds with probability 2 to the minus 32n, but it's not amplified. Okay, it's essentially not amplified, and I mean, this repeating is actually not good enough. So how much time do I have?
10 minutes.
Okay. So the thing here is that there, yes.
Can't we like do a random linear map on it that B doesn't?
Okay, yeah, that's going to be the solution.
Oh,
yeah,
okay.
I just want to to give intuition before that, but yeah, you're right basically. Okay, so I have here another example which shows that actually, yeah, even if you shuffle the rows randomly and you truncate randomly the columns, then it's not good enough. I mean, B can still correlate its answers I'll tell you, I mean, I don't want to spend too much time on it, but basically, if you do this, if you also, I mean, you shuffle the rows at random and truncate the columns at random, then what we can do is actually output a k-XOR that has a low Hamming weight vector. Okay, and you don't you can see, I mean, doing some calculation that this also the answers of B would also be correlated for different runs, because if you have like 3 vectors in the big matrix that happen to be, I mean, they're not necessarily k-XORs, but they're kind of close to being a k-XOR. And if you look at their truncations at different at random places, then they most likely will be a k-XOR in the dense instance, and they have a higher probability of being output. Okay, so it's not very important, but in any case, it's not sufficient. It's not sufficient randomization, and we need stronger randomization, basically. We need stronger randomization here to full B. And yeah, so what you suggested is basically correct. So the final algorithm is going to be the following. We repeat 2 to the 32 n times. So in each run, we define this dense matrix Y. By the following, we're going to shuffle the rows of X randomly. We're going to select a shrinking full rank random matrix, L. Okay, so it's going to shrink vectors of n bits to smaller vectors of n prime bits. And we apply it basically to each row independently, to each row of this column independently. Okay, and that's how we get this, thin matrix Y. Okay, okay, so there's an equivalent formulation here. I mean, it's not very important, but basically you actually don't even need to shuffle the rows here. What you can do is you can do the same thing. You can select this shrinking full rank random matrix of this dimension. You can define yi in this form just by applying this linear transformation to every row, and you can sort the rows of y. Okay, you can just sort the rows. It doesn't matter because, I mean, in this algorithm, you shuffle the rows randomly, but B can actually, the algorithm B can just take the random shuffling of the rows and could just sort it himself. So it doesn't, I mean, this algorithm and this algorithm are essentially the same. Yeah, it doesn't really matter. Okay, so you can show basically, again, that the success probability here in each iteration is 2 to the minus 32n. That's basically is unchanged. Okay, so what we need to show is basically the independence of the different runs. That's the piece that was missing previously, because B could correlate its answers. We need to show that it doesn't happen anymore. And in fact, it is sufficient. You don't need to prove that all the runs are completely independent. It's sufficient to prove that they are pairwise independent. Like if you look at 2 runs, then what you need to show that they're not correlated. Like the chance, okay, so what does it mean to be pairwise independent? So let Y and Z be 2 inputs of B, meaning 2 matrices produced by this algorithm, generated from the same sparse instance. Okay, so what we need to show is the following. The probability that this algorithm B applied to matrix Y and the probability of B applied to another matrix X, both generated from X. The probability that both map to a 3 XORs in X, and this large, and this sparse instance X, is basically the product of the probabilities, right? The probability of this times the probability of this, which is equal to this. This is what we need to prove. Okay, and okay, so one last remark. I am going to finish in like 1 minute. One last remark that I want to show, I want to like kind of tell you is that this is not trivial to show. And why is this not trivial to show? It's not trivial because the inputs of of B are highly dependent. And you can see that the inputs of B are highly dependent by the following very simple argument that just counts the entropy. Okay, if you count, what's the entropy of Y and Z produced from the same X? So the entropy is basically, what do we need to pick at random here? We basically need to pick at random this original X. The entropy is basically the entropy of this sparse instance. And I told you that there is equivalent formulation here where you actually don't shuffle the rows. So the only thing that you need to actually pick at random besides X are these two small matrices. So the number of bits that you picked at random is basically n times 2 to the n over 3 to produce this Y and Z. On the other end, if the Y and Z were completely independent, then the number of bits that you would need to produce them is 2 times the size of the matrices, which is 0.69 n times 2 to the n over 3, which is much larger than this. Okay, so the inputs of the algorithm B are highly dependent, yet we want the outputs to be completely independent. And that's not trivial to prove. Okay, so I'm not going to do it, yeah. I mean, I have 1 minute, so I said it's not trivial, so obviously you cannot, it's not going to fit. But the proof is at the paper, basically, and it actually uses heavy Fourier analysis on the Boolean cube. I mean, I'll just give you intuition why Fourier analysis is good here. Basically, Fourier analysis is good for analyzing correlations. So so the first step is actually, we have a function B applied to Y. So Y is just a matrix, it's just a Boolean matrix. I mean, and we have a B applied to Z, and we kind of need to analyze the properties of B. Okay, so the first thing actually we do is we kind of show a reduction from B to another function B prime, okay, which takes Boolean input and maps it to the reals. And then you can do some Fourier analysis, and basically by Plancharel's theorem, I mean, that's a standard theorem used in this domain, you can actually transfer like the correlations, like the problem of computing the covariance of this function to a problem of bounding some Fourier coefficients of this mapping, or this modified mapping B prime. And yeah, that's kind of the very, very high level intuition. But like I said, yeah, I don't have time to do this. So yeah, that finishes, I think, this part. Okay, so let me just conclude in 1 minute. So basically, I've shown you, yeah, I started this morning. I talked about kind of, very basic algorithms for 2 XOR or 3 XOR, showed some application to real-world cipher like GA1 that kind of use similar techniques. And finally, I kind of showed you a kind of interesting reduction that if kind of one algorithm for, for a specific parameter regime is optimal, then an entire class of algorithms is optimal. Okay, so these k-XOR problems have a lot of interesting applications, and and I think there is still a lot of interesting things to be discovered. For example, this is kind of a recent result. This is just from last year. Okay, so I hope I convinced you that the problems have, are sufficiently interesting, and I only talked about k equals 2 and 3. I didn't even get time to talk about k equals 4, but yeah, that's how it is. So, so thank you, and